We're going to go off to chapter 12. We're going to talk about bonding. We're going to talk about both types of bonding in this chapter. We'll also talk about molecular geometry and polarity. There's really two types of bonding we're going to talk about in this chapter, and one is ionic bonding, and one is covalent bonding. And as we'll talk about, really the difference between these two, or the really main difference between these two, is one does not involve sharing electrons and one does. So ionic is no sharing of electrons. Covalent bonding is sharing of electrons. And as we'll talk about, even with sharing of electrons, it may be equal sharing, maybe unequal sharing, but there's some aspect of sharing of electrons when we're talking about covalent bonding. And ionic bonding, there's absolutely no sharing of electrons. So let's get into this then. When we sort of represent bonding, and a lot of times the way that we do so is we use Lewis dot symbols. They are sometimes just generically called electron dot symbols. But when atoms basically interact to form a chemical bond, as we know, the electrons are on the outside of the atom, and it is really only the electrons that are involved in bonding. We don't play anything or use anything that's in the nucleus involved in bonding. And that's why, as we talked about, we sort of have conservation of our elements along the way in a chemical reaction, because it's really only electrons involved where we break bonds and make bonds, and that will never change sort of the elements that are involved. Now, there's also really a specific type of electrons that are involved in bonding, and those are the valence electrons. And the valence electrons are the outermost electrons, highest energy level. So, for example, if we look at something like sodium, which has 11 electrons, we could write what's known as electron configuration, which is chapter 11. 1s2, 2s2, 2p6, 3s1. And these represent really where all of sodium's 11 electrons are placed in orbitals within the atom. And the numbers in front here, these numbers are what are referred to as the principal quantum number, which is a fancy name for really the energy level. And something at like a first energy level, which is n equals 1, is the lowest in energy. And as you go up above that, like n equals 2 through 7, those are higher in energy. And that is what basically this number represents. That'd be n equals 1, n equals 2, and so forth as you continue down through the electron configuration. So when we look at really sodium's electron configuration, it is this very last electron here, which is this number up on top, is how many electrons there are. And that would be its valence electron. The rest of the electrons down here are what are referred to as core electrons. And core electrons are closer to the nucleus, which means that they're held a lot stronger and they're not involved in bonding. So it's only those outermost electrons that are involved in bonding. So here with sodium, it's got like 10 sort of core electrons, which are too close to the nucleus to be involved in bonding. It has just that one electron that's going to basically be involved in bonding. So to show valence electrons, we keep track of them by using Lewis dot symbols. And really, obviously, we haven't talked about electron configuration yet because they moved that chapter to the end of the semester, but we will. But the easiest way to figure out valence electrons is actually by the periodic table. And if you go to the periodic table, the group number equals the number of valence electrons for everybody. So everybody in group 1 has 1, 2, obviously 3, 4, 5, 6, 7, and 8 over here. So the number of valence electrons equals the group number. And that goes for everybody on the periodic table. We really don't play with transition metals in terms of bonding and stuff like that, so you don't have to worry about those. But again, these are representative groups, or group 1, 2, again, skipping the middle, 3, 4, 5, 6, 7, and 8. The one exception to that is helium. Helium is a member of group 8, but it has only 2 valence electrons. That's because helium only has a total of 2 electrons total, so it can't have 8. So all others there in group 8 will have 8 valence electrons, except for helium that has only 2, which is all 2 of its electrons. So it does consist of basically the symbol. So we use the proper symbol here. And we basically use 1 dot to represent each of the valence electrons when we're talking about bonding. And there's really kind of no rule per se, other than typically speaking, you don't go more than 2 dots per side. So you'd be more than 2 dots per side. A lot of people will do 1 dot kind of around clockwise and then kind of pair everybody up, but it really doesn't matter as long as you kind of don't do more than 1 dot per side. That's 2 per side. There's 4 sides. That's 8 electrons. And on the periodic table, who has 8 electrons? Group number 8, which is noble gases. As we'll talk about, that is really the whole point of bonding. The whole point of bonding is for everybody to achieve noble gas configurations. So ionic bonding, covalent bonding, both types of bonding that we'll talk about, the ultimate goal for all those guys is to achieve noble gas configuration. So what that means is they end up with the same electron configuration as a noble gas, and that's because noble gases are really, really stable. So that's the goal of everybody, to sort of achieve that stability. They do not change into noble gases. So they don't change elements, and that is again because we don't do anything with the protons, right? Protons is what determines what element it is. So in this case, we're just getting these guys to the same electron configuration as a noble gas, and that makes them very, very stable in this situation. So here's a look at some Lewis dot symbols, and as you can see, everybody in group 1 has 1, 2, 3, 4, 5, 6, 7, 8. Again, except for our helium here that has 2. This is also a really important thing about bonding as well. Everybody tries to get to noble gas configuration, and our good friend hydrogen only needs to get to helium. So when we're doing bonding with hydrogen, it should never have more than 2 electrons ever. Yeah, so hydrogen should always kind of look like this. It's like a line and a H there, should have no dots around it, no double bonding, triple bonding, or anything crazy like that. Triple bonding and putting dots around it, you know. So I'll emphasize this because people always screw this up. They just like want to keep piling things onto hydrogen. So that's just going to get you a big X. Yeah, so don't do that. Again, hydrogen really, as you look at the periodic table, only needs to get to helium. All other elements, pretty much the goal is to get to these guys over here again in group 8 in terms of their electrons is really the goal of it. And it's achieved in 2 different ways, through ionic bonding, by transferring electrons, and in covalent bonding through sharing of electrons. They're able to achieve that noble gas configuration. Any questions on that there? All right, so let's talk about the 2 really different types here. Lewis dot symbols helps us understand 2 types, which are ionic compounds. So if we have an ionic compound, that is going to be a metal and a nonmetal together. And what's going to happen is the metal will transfer electrons over to the nonmetal. The result of that is the metal will become a cation, which is positively charged. The nonmetal will become an anion, which is negatively charged. And it is that electrostatic attraction that holds that together. So again, here, there's absolutely no sharing of electrons that's happening. There's the positive charge from the cation attracted to the negative charge of the anion. And that's a pretty strong attractive force, and it actually increases with the charge. So again, it's something that's +3 and -3 would be held together stronger than something that is +1 and -1. And that's different than covalent bonding or covalent compounds. That is always between 2 nonmetals. And really, the reason why it's between 2 nonmetals here is we do end up actually with sharing of electrons in this case. And the sharing could be equal. nice equal sharing of electrons or unequal sharing of electrons. But there is some aspect of sharing that's happening here in a covalent bond. And really the reason for the difference is a lot about sort of periodic trends, which again, unfortunately, they moved it to chapter 11, which is out of this. This is out of order now. But we'll borrow this periodic table here and talk a little about some of these periodic trends to help us understand sort of what is going on. And then officially we'll talk about it in chapter 11 when we get there. But in terms of periodic trends, there's a couple important ones that sort of help us understand what happens when we look at the periodic table and why things either will give away electrons and why things will sort of share electrons, for example. One thing is what is known as ionization energy. And ionization energy is the energy needed to remove an electron from the gas phase. And when we look at ionization energy, it actually increases as you go this way. So ionization energy increases. And it decreases as you go left and down on the periodic table. There's also something that is known as electron affinity. Which is the energy change when an atom gains electrons. So if you think about ionization energy, it's when somebody kind of loses electrons. That's what happens when something becomes a cation or positively charged. And electron affinity, if you have an affinity for something, you like it, right? So electron affinity is the energy change when somebody gains an electron. And that is, again, what happens when we make an anion that becomes negatively charged. In terms of electron affinity, it's not a perfect sort of pattern, but it also increases as you go this way and decreases as you go this way on the periodic table. There's also another sort of pattern, which is electronegativity, which we'll talk a lot about in this chapter. And again, that is different than electron affinity. That's the ability of an atom to bring electrons towards itself. And that increases as you go up and to the right. And decreases on the periodic table as you go down. By the way, the most electronegative is this guy right here. He is the most electronegative you could have, which is fluorine. And a couple other trends which are sort of important is atomic size. And in terms of atomic size, which is the size of atoms, it gets smaller as you go up and to the right and gets larger as you go down and to the left. So size. So these periodic trends, which again are in chapter 11, we'll talk a little bit more about it as we kind of go through that chapter when we get there, really tell us what happens when we get things that come together for bonding. When we go up and to the right on the periodic table, we have things that have very high ionization energy, which means it takes a lot of energy to remove electrons. We have things with high electron affinity, which means they like to gain electrons. We have things with high electronegativity, which means they like to gain electrons and take electrons from other people. And they have things that are very small in size, which means even their outer electrons, because the overall size is small, is going to be much closer to the nucleus, which is why they have high ionization energy. It takes a lot of energy to remove those because it has a very strong attraction to the nucleus. So what that tells us is everything upper right of the periodic table, which is typically our nonmetals, like to gain electrons and not lose electrons. And if we go kind of on the other side, left and down on the periodic table, We have things that are much larger, which means their outer electrons are further away from the nucleus, not held as tightly. And that means it doesn't take a lot of energy to remove an electron, so they have low ionization energy. They also have very low electron affinity and electronegativity, which means they're not interested in gaining electrons or bringing electrons towards themselves. And that's why when we go left and down on the periodic table, where our metals are typically the guys that will like to lose electrons. So metals typically like to lose electrons because of these periodic trends, and nonmetals like to gain electrons because of their periodic trends. And this is really the basis of what happens when we get these two types of bonding that occurs. Ionic bonding, which is a metal and a nonmetal. That is why we have a transfer of electrons from the metal to the nonmetal, because pretty much they have opposite ends of that spectrum. Metals want to give away their electrons. Nonmetals are like, cool, thanks, we'll take them. And we get a complete transfer of electrons. When we get in a covalent bonding, two nonmetals together, all nonmetals, if you remember right, are pretty much in that area right there on the periodic table, which means everybody in that bond wants to hang on to electrons. They actually want to take other people's electrons. So what happens when two guys get together, there are nonmetals, the best they could agree upon is we'll just share the electrons. I'm not going to give away my electrons. You're not going to give away your electrons. They will share electrons. And that is what happens in a covalent bond versus an ionic bond, where you have one guy just like, take my electrons, and one guy's like, cool, I'll take them. And that's, we get those transfer of electrons. Any questions on that? Yeah. Say it again. What happens when it loses one? And group one, it will become a cation, which is a positive one charge. So I think we talked about things when they gain charges and stuff in here when we were talking about, I think, protons, electrons, and neutrons, atomic numbers. So remember, it's just the electrons that change, right? When somebody gains a charge. So for example, something like sodium, it will always give away one electron because that's its valence electron. It's easy to give away. When you go from its valence electron and then say its 10th electron, you want to give away one more electron to give it a +2 charge. That's its core electrons, which means it takes a super high amount of energy that usually doesn't happen. So that's why something like sodium will always form a +1 charge, because that's the only electron that's very easily allowed to sort of go away. Other questions? And that happens a lot, and that's why ionic compounds form, because when a nonmetal is in the vicinity, it's like, cool, I want your electron. So it's going to want to bring that electron towards itself. Sodium's like, go ahead, I'm not going to hold on to it that tightly. And it's going to be able to actually fully transfer. And that's different than when we get into our covalent bonding. When we got guys in this range, they both really want to hold on to electrons and bring electrons towards themselves. So that's why I said the best they can do with covalent bonding is to share electrons and sort of be happy at that situation. Other questions? All right, so that was a tangent to chapter 11, which we'll talk about again later on, but it does relate here. So covalent bonding, like I said, sharing of electrons, and as we'll talk about, maybe equal, maybe unequal, but definitely sharing. Ionic bonding, no sharing. And by the way, always know it's an ionic bond whenever it's a metal and non-metal involved. So don't have to worry about it, don't have to think about it. It's ionic. You have metal, non-metal. That's definitely the way you distinguish that type of bonding. So in general, low ionization energy, as we talked about there, are that ability or that energy needed to remove an electron. They tend to have really low ionization energies and they form cations. Guys with high electron affinities means that they like to gain electrons, and those are typically our nonmetals. So that tells us that pretty much elements on the left-hand side there, group 1 and group 2, will form cations. On the upper right there where we have our nonmetals, that's where we would expect our negatively charged guys to be formed. So let's take a look first at ionic bonding, which is lithium fluoride is an example of that. So if we look at this, which is ionic bonding. And by the way, I do know this is ionic because lithium is a metal. Fluoride, which is fluorine, is a nonmetal. And pretty much that combination always results in an ionic bond being formed. That means that we are going to have basically a transfer of an electron from our lithium, in this case, to our fluorine. So if we look at lithium, lithium is group number 1 on the periodic table, which means it has 1 valence electron, which is that dot right there. And again, we haven't talked about electron configuration, but I'm going to write the electron configuration so we can kind of see it. 1s2, 2s1. And by the way, that is the 1 valence electron is the electron on the 2nd energy level. That is the valence electron in the case of lithium. If we go to fluorine, which is group 7, it has 7 valence electrons. And once again, I'll write the electron configuration for fluorine: 1s2, 2s2, 2p5. And these are the 7 valence electrons, as they are both on the 2nd energy level here for fluorine. That is fluorine's 7 valence electrons. They happen to be in an s orbital and p orbitals, which we'll talk about when we get to chapter 11 as well. So what we have here is our metal and our non-metal. And what's going to happen is our metal is going to transfer its electron over to our non-metal. So this electron here will get transferred over. The result of this is lithium has now lost an electron, and at that point it will become positively 1 charged because it gave away its electron. And the fluorine here actually has room for it right here. A p subshell could actually hold 6 electrons. It has only 5 right there, so it's got room for it in this case. So it actually will put its electron there. And what will happen is our fluorine here will pick up that electron, and it will now become a negatively charged here. And when we draw Lewis structures for ionic bonding, which is what we're doing here, we should always show the charges. The charges indicate that there is no sharing of electrons in this case. We have a transfer of electrons. We have charges that have been made. Now, again, what happens in this particular case is their electron configuration is adjusted because they lost an electron, gained an electron. So what happens to lithium is it pretty much gave away this electron right here, which means with a +1 charge, it has an electron configuration of 1s2. Who on the periodic table has 2 electrons? 2 is helium, yes, and helium is a noble gas. So lithium here, by giving away that electron, now ends up with the same electron configuration as helium, which is a noble gas, and that makes it really stable. When we look at fluorine here, which gained an electron, it ends up with an electron configuration of 1s2, 2s2, 2p6. That is where the electron ended up. And if we add up all these electrons, as 2, 4, and 6 is 10. Who on the periodic table is 10? It is neon's configuration. So in this case, fluorine, by accepting that electron, now has the same electron configuration as fluorine. And that is actually the goal of bonding, is for them to end up again with the same electron configuration as a noble gas. This, by the way, means the noble gas configuration. They are said to be what is referred to as being isoelectronic. Isoelectronic means that they have 2 things that have the same electron configuration. So lithium with a +1 charge is isoelectronic with helium, and fluoride, which is fluorine with a -1 charge, has the same electron configuration, or is isoelectronic with neon. They have basically the same electron configuration. So in this case, because of their wide separation in terms of their periodic trends, the metal is willing to lose its electron, the non-metal is willing to accept the electron, creates a whole positive charge for the metal, negative charge for the non-metal. And it is that attractive force between the positive and negative charge that actually holds that together. Once again, no sharing of electrons here. Any questions on that there? So I think what it says. There we go. That's what we just drew. Perfect. So that is pretty much what an ionic bond is. It is the bond that holds together really the cation and the anion, and is that really strong attractive force, which is sometimes referred to as electrostatic attraction between the oppositely charged ions in this case. Take a look at another example, calcium and oxygen. So once again, calcium is a metal. Oxide, which is oxygen, is a nonmetal. So once again, when I see that combination of metal and nonmetal, I again know that this is an ionic bond that's going to happen in this case. And again, we're going to get that transfer of electrons from the metal to the nonmetal in this case. So if we look at calcium, calcium is group number 2 on the periodic table, which means it has 2 valence electrons in this case. And I'll write the electron configuration for this, which is argon 4s2, R1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So this part of it right here, by the way, just so we know, if we add up all those right there, the top numbers, that is 2, 4, 10, 12, 18 electrons. And 18 electrons represents argon's electron configuration. So that's what the little bracket and the argon means, is the electron configuration of argon. And then you kind of continue on with the rest of it there for calcium in this case, which is 4s2. It's going to go with oxygen, which is group number 6. So it's got 6 valence electrons here. And it has an electron configuration of 1s2, 2s2, 2p4 in this case. And the 6 valence electrons are these guys on the second energy level. 2 and 4 is the 6 valence electrons that we see represented as dots in this case. Again, the lower electron there, the 1s2, is again the core electron, not involved in bonding. So it's only the valence electrons that are involved, are shown in Lewis structures. By the way, they still have the other electrons. They're just not shown, obviously, in the Lewis structures, which is involved in bonding. So in this case, we have our metal and we have our non-metal coming together. And what's going to happen is calcium's going to give away an electron here. And in this case, if calcium only gave away 1 electron, it would move where on the periodic table? It would end up at 1 electron less, would move it to potassium, right? Which is not a noble gas. So it does want to give away both of its valence electrons because it needs to move. If you look at the periodic table, it needs to move back 2 spots to get to argon in this case. So this will then lose both of its electrons. And in this particular case, at that point, our calcium will now have a +2 charge. The oxygen will gain those 2 electrons. And because it gained 2 electrons, it now has a -2 charge. And what happens in terms of its electron configuration is these are the 2 electrons that calcium gave away. So these 2 electrons go away. And that leaves it with just 18 electrons, which is 1s2, 2s2, 2p6, 3s2, 3p6, and that is the same as argon's configuration. So here again, calcium is able to achieve noble gas configuration by offloading its 2 electrons. And what happens to oxygen is, again, a p subshell could actually hold 6 electrons, so it actually has room for 2 more in there, which works out really nicely. And oxygen with a -2 charge, which is oxide, has this electron configuration, and that is 6, 8, 10, and that is neon's configuration. So once again here, by losing and gaining electrons, both of these elements are able to achieve the same electron configuration as the noble gas and be very, very stable. Any questions on that there? Once again here, we do put the charges. Sometimes we bracket both of them, or at least one of them, with some brackets, just to show again that there's no sharing of electrons that are happening here in an ionic compound. Any questions on that? Now, what happens if we take these two guys in these two examples here and put them together? So let's just say we took, our calcium, which has 2 valence electrons, which again is our argon 4s2. And let's put it together with fluorine that has its 7 valence electrons and an electron configuration of 1s2, 2s2, 2p5. So when this happens, our calcium is going to want to give away its electrons. And when it does, it's going to send an electron over here to fluorine. At that point, can that fluorine take any more electrons? It cannot. Again, it can only have 8, right? And this guy could only hold 6, which means it's pretty much full at this point. That is good for fluorine because it gets it kind of full. Not so good for calcium, as we were just talking about. By calcium just losing 1 electron, only gets to potassium, which doesn't have the same ring as a noble gas configuration. The alkali metal configuration doesn't sound the same, so it's not right what it wants to do. So in this particular case, we actually would need not 1 fluorine, but we would need a second fluorine. And a second fluorine has room basically to take the second electron there from calcium. Now calcium is able to get rid of both of its electrons, 1 to each of the fluorine. The result of that is it's going to get rid of both of those valence electrons, and it will achieve argon's configuration. We will then end up with a fluorine that gained just 1 electron, which means it has a -1 charge. And we would end up with a second one. I'll just draw it here since I'm running out of room below. That also gain 1 electron that will also have our -1 charge. Each of those fluorines put an electron into here, which means they each end up with 10 electrons. So both of these guys end up with the same electron configuration as neon. So all 3 of those things basically have now achieved noble gas configuration. Perhaps you remember, I think we talked about at the end of the last chapter, maybe, that whenever you put together something that has a positive charge and a negative charge in a formula, right, we want the charge to balance out to 0. And this is really the reason why, because if we take something like calcium and fluoride, we need 1 more of these guys to get us to no charge, and that is the proper formula for calcium fluoride. The real reason is when we put together something that's a positive charge and negative charge, which is what happens in an ionic bond, we do it in the simplest way possible to get to 0. And what that essentially does is it allows everybody to achieve noble gas configuration. So it's really the bonding part as to why we put it together to end up with a 0 charge. It allows everybody to make a proper ionic bond, allows everybody to achieve noble gas configuration. Because clearly, if we put it together without doing that and ended up with something like this, that is going to mean that the calcium did not reach noble gas configuration, right? So he needs to offload that second one. And that's really the whole point behind when they tell you in naming and writing chemical formulas for ionic compounds that it has to equal 0 in the simplest way possible. It's really the bonding aspect of really why that is, so that everybody gets to that stable configuration and makes a stable ionic bond. Any questions on ionic bonding here? So this is how we can show ionic bonding using Lewis dot symbols. And once again, you do need to make sure that there are charges on these on the back end there to indicate, again, no sharing of electrons. All right. So then let's talk about the other type of bonding, which is covalent bonding. So covalent bonding is between 2 nonmetals. And because the 2 nonmetals, once again, pretty much are over here in the same spot on the periodic table, they have the similar periodic trends that we talked about. They have very similar electronegativities. They have similar ionization energies. this is the case where we were talking about earlier that the best that they will do is share those electrons, because neither one of them wants to give away the electrons. They both want to hang on to their electrons and hold on to them. So Gilbert Lewis, hence Lewis structures, suggested the idea of covalent bonding as really the sharing of electrons between two atoms. So if we take a look at our hydrogen here, they each have one valence electron. And because they're both obviously hydrogen in this case, neither one of them is going to give away its electron because they have the exact same periodic trends. So what's going to happen is we're going to make a bond between those two hydrogens where those electrons are going to be shared equally. We could represent it like this with two dots. We could also represent it like this with a line. One line represents two dots, which is a single covalent bond. Two lines, as we'll see, represents 4 electrons or 2 pairs of electrons, which is a double bond. And 3 lines represents 6 electrons or 3 pairs of electrons, which is a triple bond. So in this case, as we were talking about, they're going to share electrons to basically be happy. And that means that those electrons that are being shared between the two hydrogens count for each hydrogen. So the hydrogen on the left gets to count them, and the hydrogen on the right gets to count them, which means both of those hydrogens now have 2 electrons. And that's really good for hydrogen because, again, if we look at the periodic table, the element packed hydrogen, that's a noble gas, is helium. So again, hydrogen just needs to get to 2 to be happy, and that's going to make it very happy and a nice bond that's going to happen there. So this type of bond where we have sharing of electrons is a covalent bond. The electrons are kind of attracted to the nucleus of one atom and the nucleus of the other atom, and they're negatively charged. So that's sort of what locks them in place between the two atoms, is that mutual sort of attraction between the two nucleuses. And again, by sharing of electrons in a covalent bond, that's going to allow these elements to reach that noble gas configuration and be really sort of stable. Any questions on that there? A reminder as well that hydrogen is a nonmetal, right? So in a covalent bond, as I mentioned, that mutual attraction between the two positively charged nucleuses is what's going to hold those negatively charged electrons kind of between the two atoms. And again, that is a covalent bond, which is sharing of electrons. And as we'll talk about, maybe equal or unequal sharing, but again, some aspect of sharing is happening in this situation. So let's take a look at fluorine. Once again here, if we look at fluorine, it has 7 valence electrons, which is what we see here, and 7 valence electrons. So these two guys are going to share electrons between them. And the result of that is we can create 2 types of bonds here, or 2 ways you could show the bond. You could show it with all dots like we see here. Or you can show what is referred to as those electrons involved in a bond with the line. And the other ones as dots. But if we look at what has happened in this situation by sharing electrons here between the 2 fluorines, the fluorine on the left here has 8 electrons. Fluorine on the right, also by sharing those electrons in the middle there, has 8 electrons. And once again, that 8 is a very important number, obviously, in bonding. It is where the noble gases are in terms of their electron configuration. And that is, again, the goal of covalent bonding as well, to get everybody to that noble gas configuration of basically 8 valence electrons. Any questions on that there? And again, for fluorine, this would be the 7 valence electrons that we see in each of those guys. Now, when we look at a Lewis structure such as this for something like fluorine, there actually are 2 different types of electrons which are important, especially going forward as well when we talk about geometry and stuff like that. And to know the difference between them, let's talk a little bit about the different types of electrons that we see in this picture. All the electrons that are not involved in any type of bond, which is pretty much all the dots in this picture, We know that they're not involved in any bond because there is no element on the other side of those dots. So there's nothing there. So it's not involved. These are what are referred to as non-bonding electrons. If you're old like me, they'll call it lone pairs, and I probably will call it lone pairs. So lone pairs and non-bonding electrons are the same. I would say most books nowadays use non-bonding electrons, but people still use lone pairs a lot, and I probably will say it as well. Now, the other type of bonds that are electrons that are there are these electrons right here, which is involved in a bond formation, and they have a creative name known as bonding electrons. So we have bonding electrons, which are obviously involved in a bond. We have non-bonding electrons or lone pairs, which are not involved in bonding. Whenever you draw your Lewis structures, you should always draw all of those type of electrons. So you should always include the non-bonding electrons, should always include the bonding electrons. Non-bonding electrons for us should always be dots. Nothing else, no lines or anything like that. So they all should be dots. Bonding electrons is it's your call, whatever you want to do. If you want to use dots for the bonding electrons, you can. If you want to use lines, you can. I personally use lines for bonding electrons, and a lot of people do. But it's not necessarily wrong if you want to use dots for non-bonding for bonding electrons as well. So you could use the dots if you want to use them. But most people use lines for those bonding electrons. Any questions on that? So again, a Lewis structure is a representation of covalent bonding, where again, we show those lines for our bonding ones, the dots for our lone pairs. A reminder again, that it's only the valence electrons that are shown in these pictures. They still have those lower energy level electrons that are not involved in bonding, but it is only those outermost electrons that are involved in bonding, which again, you could calculate the number of valence electrons by just taking the group number from the periodic table. Well, it's the much faster way to figure those out. Another example here of water. When we look at water, by sharing electrons with each of the hydrogens here. The oxygen here, by sharing those electrons with the hydrogen, is able to get to 8 electrons. Each of the hydrogens, by sharing with the oxygen, are able to get to 2 electrons. And by, again, sharing electrons here, all 3 of those elements have basically reached that noble gas configuration. The hydrogen's got 2, and that, again, is all it needs. And our oxygen here has 8 electrons, and that is what it needs to be sort of happy. When you look at these Lewis structures here, there's no charge. So a reminder that the only things that have charges when you draw Lewis structures are ionic compounds. These are covalent compounds, which means sharing of electrons, no charges happening, and there should be no charges in any of these sort of pictures that are covalently bonded together, unless it happens to be an ion. But so that brings us, obviously, as we've been pretty much talking about as we've been going through this, the 2 major rules for bonding, and that is the octet rule. And the octet rule means that everybody will continue to make bonds until pretty much it has 8 valence electrons around it, which makes it, again, very stable. The exception to that is hydrogen. And again, hydrogen should only, I'll say it one more time, only have 2 electrons. So once again, pretty much, as I showed earlier, your hydrogen should only look like that. Also should mean that you should never see hydrogen in the center of the molecule, because if it's in the center, it's going to have more than 2 electrons. So hydrogen should always be on the outside, pretty much one line to it, and that's it. And that's because, again, hydrogen has the duet rule, sometimes referred to, which means it just needs to get to helium in terms of its electrons. Now, as we'll talk about, sometimes, it requires a single bond to kind of get to the octet rule. Sometimes it may require a double bond or a triple bond to sort of get to the octet rule. But in most cases, as we'll talk about, you really shouldn't, in most cases, double bond or triple bond out of the box, which is a very common mistake that people make when they start drawing Lewis structures for covalent compounds. they want to like double bond and triple bond because it looks more chemistry like and stuff like that, you know. So a lot of times we want to kind of save us. We'll talk about double bonds or triple bonds to sort of fix a situation where somebody has not reached the octet rule. So in general, we don't really want to kind of double bond or triple bond usually right out of the gate. We kind of want to save that, and we'll talk about the sort of order at which you should draw these things. But a single bond, as we talked about, is basically sharing of one electron pair, which again is 2 electrons total, and that would be 2 dots. Now, sometimes like here with carbon dioxide, it needs to, as you can see there, pretty much make a double bond on both sides to actually achieve the octet rule. That gives the carbon in the middle 8 electrons, gives the oxygen on the right 8 electrons, and gives the other oxygen on the right 8 electrons in this case. And that gets them all to basically meeting the octet rule. And a double bond, once again, is 2 lines are 2 pairs of electrons, however you like to sort of show it. And as I also mentioned, you know, in some cases, that's what you need to do to reach that octet rule. And in some cases, you need to go kind of a step further and get yourself to a triple bond to reach that sort of octet rule. So a triple bond here looks something like this. And it is basically 3 lines are 3 pairs of electrons. By the way, when you draw a triple bond, you do need to do a stacking situation, not just like dots in a row or anything like that. So it does need to be sort of stacking if you use dots. So something like nitrogen here, each of these nitrogens, by sharing actually those 6 electrons between each of them through that triple bond, is able to achieve that noble gas configuration. And here with ethine, which is acetylene here, our carbon also through sharing that triple bond and also sharing with hydrogen on the outside as well, is able to achieve 8 electrons. And in that case, each of our hydrogens also achieves 2 electrons, which is exactly what it needs. Any questions on that there? Okay. So we're talking about here covalent bonding and sharing of electrons. So what helps us determine how these electrons are going to be shared? Again, they may be shared equally, they may be shared unequally, and depending on how they are shared gives you a different type of covalent bond. And really the overwhelmingly sort of trend that we look at to help us decide how these electrons are going to be shared is actually that electronegativity. So as we talked about earlier, electronegativity is the ability of an atom to attract electrons towards itself. And once again, that general trend is increasing up and to the right on the periodic table, with fluorine being the most electronegative and decreasing as you go down and left on the periodic table. So it's actually the electronegativity that really determines, when you look at 2 atoms together, how those electrons are going to be shared. They're going to be shared equally, going to be shared unequally. And let's take a look and see how we could use that to help us decide. So when we look at something like hydrogen in this particular case, that H2 bond, if we have hydrogen here, because hydrogen again is the same element, we would expect that these electrons would be attracted to each of the hydrogen atoms pretty equally. The pull of that positive charge within the hydrogen is going to pull those negatively charged electrons sort of equally in both directions. The result of this is, if my little smear here is the electron distribution, we're going to end up with a pretty equally shared electrons. So we're going to end up with equal sharing of electrons. And this is going to make what is referred to as a nonpolar covalent bond, or most people just call it a nonpolar bond. it's implied that it's covalent, there's sharing of electrons. So what happens in this sort of particular case when we get these electrons to sort of share equally between two atoms is there's kind of like no charge. And what I mean by that is electrons are negatively charged. So they're going to be evenly distributed over the bond, which means there's not going to be a side to that bond that is kind of more positive. There's not going to be a side that's more negative because we have nice equal sharing and distribution of those electrons. You could kind of think of it almost like a neutral bond. So there's like no like charge is going to develop because those electrons are just going to be shared sort of equally between them. And that is a nonpolar bond. A nonpolar bond always for sure occurs when you have two of the same elements involved in the bond. Obviously, again, because they have the same electronegativity values and ionization energy values, because they are basically the same element, you would expect them to be shared equally. Sort of like if you took a string and kind of two people pulled equally on the string, it's not going to go anywhere, right? Or anything like that. So there's just going to be a nice even distribution of it. Now, what happens when we take something like HF? We take something like HF. Now, when we look at this bond, there is actually a difference between the electronegativity value of hydrogen and fluorine being the most electronegative element you could have. Fluorine is going to go, I would like your electrons, and hydrogen is going to try to hang on, basically, is what's going to happen. So in this case, what's going to happen is because fluorine is more electronegative, we're going to get really a buildup of electrons kind of hanging out on the fluorine side and not so much hanging out there on the hydrogen side. And the result of that is we actually will get a separation of charge in this case. And the fluorine side, because it's going to attract electrons closer to itself, would you expect the fluorine side to be more positive or more negative in this case? The electrons are going towards the fluorine, it should be more negative because electrons are negatively charged, right? So electrons are hanging out closer to the fluorine, and it will create a partially negative charge, and that's a delta symbol there, negative. And the hydrogen, because the electrons are basically going away, is making a partially positive charge. So partially positive. Partially negative. We could also represent this very commonly when we talk about bonds, and this is what is sometimes referred to as a bond dipole arrow, where we make an arrow that points to the more negative side of the bond. So it always points to the more negative side. And the back end of the arrow kind of makes a plus sign, is to the more positive side of the bond. So sometimes you'll see these arrows drawn to indicate that there is unequal sharing of electrons that's happening here. Now, why is it only a partially positive charge and a partially negative charge and not a full positive charge and a full negative charge in this situation? What do you think? How are the electrons here? The electrons are being what? Shared. Yeah. So since they are still sharing those electrons, we don't get a full positive charge or full negative charge. They're partially positive and partially negative because hydrogen is kind of still hanging on, kind of like the rope example. Now you got somebody pulling really strong on one side and the guy's just kind of hanging on for the ride, right? But he's still hanging on as he's being dragged around the corner there. And that's sort of what's happening here with hydrogen. It's still being able to hang on to its electrons, but definitely not equally. And it's still some aspect of sharing that's happening here. And that's why we create partially positive charges and partially negative charges. That is different than what we see with an ionic bond. In an ionic bond, because we have a metal and a non-metal, the metal is not hanging on for all dear life. It's just letting go, and it's going to let go of its electrons. And that's why the metal becomes fully positively charged in an ionic compound, and the non-metal becomes fully negatively charged in the ionic compound because it fully gains those electrons. So that is the difference between sort of the charges that we sometimes see here with an ionic bond versus a polar bond, which does have sort of charges, but they're partial charges because there's still some aspect of sharing that's happening here. Question on that there. Now, this type of bond is what is referred to as a polar covalent bond, or just simply most people just call it a polar bond. So when you hear somebody say polar bond or non-polar bond, it's implied again that it's a covalent bond and sharing of electrons. That's really the only place where that happens is in covalent bonding, polar bond and non-polar bond. So the full name is polar covalent, non-polar covalent, but most people again just call it polar bond and a non-polar bond. And an ionic bond implies no sharing of electrons between them. Any questions on that there? So again, we get this sort of distribution that can be represented by this bond dipole arrow. And again, that is very commonly seen a lot. And the availability of things like these partially positive charges, partially negative charges, have a very big effect, and even in the absence of those in a nonpolar sort of bond, on some of the properties that certain molecules can have, how they can interact with themselves, how they can interact with other molecules. Either there are those charges or they're not there. And it does have a pretty big effect on, kind of how molecules interact with one another. As I showed before there's our partially positive charge and partially negative charge. So to summarize the three different types of bonding, on one end of the extreme, we have our ionic bond. That is always between a metal and a non-metal. And we always have a transfer of electrons from the metal to the non-metal, creating our cation that is positively charged, that comes from the metal, and our anion, which is negatively charged, which comes from the non-metal. And again, it's that electrostatic attraction that holds that together, no sharing of electrons. And again, an example would be something like sodium chloride, for example. On the other end of the extreme, we have a non-polar covalent bond. Or just a non-polar bond. That's between two nonmetals. That is equal sharing of electrons. And an example would be something like our F2, our H2 that we saw along the way. And in the middle there, we have a polar covalent bond, which is also between two nonmetals. And it is unequal sharing of electrons. And an example obviously would be this guy right here, our HF, which obviously gives us a positive side and negative side. So on one end of the extreme, we have ionic bonding. We get the full transfer of electrons. On the other end of the extreme, we have perfect equal sharing of electrons. And in the middle, we have not equal sharing of electrons, but not so equal that the electrons actually transfer. So there is, again, that aspect of somebody hanging on to their electrons on each side, and again, creating that sort of separation of charge that occurs in a polar bond. Any questions on any of those three types of bonding? Yeah. So as I mentioned before, it really is that electronegativity that is what helps us determine whether or not those electrons will be shared equally or unequally. You could also use electronegativity to help you decide if it's going to be an ionic bond, but truthfully, you really don't need it, because as soon as you see metal and non-metal, you know it's an ionic bond, so you actually don't even need the electronegativity value to help you out. Electronegativity, as we talked about a couple of times already, again, that ability to bring electrons towards itself, and it is based on electron affinity, which is that energy change when somebody gains an electron, and ionization energy, which is the energy required to remove an electron. So things with high electronegativity have high electron affinity and high ionization energy. So fluorine has high electron affinity and also high ionization energy, and has high electronegativity, extra, I think. Sodium, which is our metal, on the other hand, has low electron affinity and a low ionization energy and has low electronegativity. So a guy by the name of Pauling came up with really a method of calculating electronegativities, and the Pauling scale goes from 0 to 4, and 4 is the most electronegative. 0, not so much. So you can calculate what's sometimes referred to as the change in electronegativity values, delta En. Delta meaning change, En meaning electronegativity. And if you calculate the change in electronegativity values and you have anywhere from 0 to 0.4, that is what is referred to usually as a nonpolar bond. So you would expect equal sharing of electrons to happen. If you calculate the change in electronegativity and you're really like kind of 0.5 to below 2, that's going to be a polar bond, and you would expect unequal sharing of electrons. And if you calculate anything typically above 2, not perfect in all cases, there are ionic bonds that are below 2, but it's going to be ionic. Once again, I wouldn't even technically worry about using electronegativity values, as I mentioned, for ionic compounds, because all you have to do is identify as a metal and non-metal, and that's good enough. There are definitely some combinations of metals and non-metals that will give you less than 2, and they're still ionic. So I would look at metal, non-metal, ionic. I would use really difference in electronegativity values to help you decide between polar and non-polar. Now, there is also a distinction that sometimes books will make for a nonpolar bond, and that's like when you get perfect equal sharing of electrons. So sometimes if you have a difference in electronegativity value and it equals 0, it is sometimes referred to as a pure covalent bond. That is still a nonpolar bond. That is still equal sharing of electrons. So that's equal sharing. That's unequal. And that would be equal sharing. So if you hear the terminology pure covalent bond, that means it's a nonpolar bond. You have equal sharing of electrons. It's like nice and perfectly equally done in terms of that sharing part of it. So let's take a look at electronegativity table here and sort of see how to use it. I have an idea. We'll use this one here. We'll blow it up a little bit. All right, so if we look at these sort of values here, we can see that on the left-hand side, we have much lower values. On the right-hand side there, we have our higher values for fluorine, for example, which is 4. So if we look at the ones that we did previously, we got sodium chloride, we got HF we were looking at, and we'll do F2, what are we looking at, right? All right, so if we were to do the electronegativity values for each of these, we'll look at sodium. So sodium right there is 0.9, and our chlorine there is 3. So we'll do our change in electronegativity, basically 3 minus 0.9. You just take the larger number from the smaller, so you get a positive number is basically what we do here. That gives us a 2.1 difference there. And a reminder that our scale is anywhere from 0 to 0.4 is nonpolar. Basically 0.5 to below 2 is polar, and above 2 is ionic. So we would see here at 2.1, we would obviously be ionic, which is what we would expect. Once again, you don't really even need the values to do that because simply it's a metal and a non-metal. If we look at fluorine, which is 4, so if we take a look at fluorine there, has an electronegativity value of 4. So that would be 4 for this guy and 4 for this guy, which gives us a change in electronegativity of 4 minus 4, which is 0. That definitely falls under a nonpolar bond, which is what we would expect to happen. And lastly, if we look at hydrogen, which is 2.1, and we look at fluorine, which is 4, the difference in electronegativity would be 4 minus 2.1, going to give us a 1.9. So 1.9 is pretty up there, yes. So that's going to give us a polar bond. And again, if we drew the arrow, it would point towards the fluorine in this case. Question on how to use that there. So why don't you try some here? Why don't we do the bond between, say, carbon and oxygen, the bond between sulfur and oxygen, the bond between carbon and hydrogen, the bond between potassium and chlorine, and the bond between carbon and sulfur. All right, so use the values here, calculate the change in electronegativity, and decide, are this ionic, polar, or non-polar bond? Let's take a look and see, since we're getting close to the end here. So we're going to take the differences in these values. So our carbon is 2.5. Our oxygen is 3.5. So our change in electronegativity would be 3.5 minus 2.5, which would be 1. And 1 puts us right here in a polar bond in this case. So this would be polar. If I were to draw that arrow, which way should it point? Towards carbon or the oxygen? Should point towards the oxygen, the more electronegative. So that is where we should draw that arrow. That means the oxygen here is more negative than the carbon in this case, which is more positive in this bond. If we look at sulfur and oxygen, sulfur is 2.5. Oxygen is 3.5 as well. So that also is going to give us here a difference in electronegativity of 1. 3.5 minus 2.5 equals 1, meaning this is polar as well. And we would expect that. If we look at carbon, which is 2.5, our hydrogen is 2.1. So if we just take the difference there in electronegativity, it gives us basically 0.4. 0.4 is the cutoff here for nonpolar in this case. And the reason for that is pretty much all organic molecules are nonpolar, and they're basically made up of carbons and hydrogens. Now, that is nonpolar. Is that perfect equal sharing of electrons? It's really not, right? So there's kind of hedging a little bit there towards the carbon, but not enough to be considered unequal. So it is still considered equal sharing, but in reality, there is still a little bit of unequal sharing that's happening there. Our potassium, which is 0.8, our chlorine, which is 3, I think. That is going to get us a difference in electronegativity of 3 minus 0.8. Looks like 2.2, I think. And that definitely is ionic. Once again here, I really didn't need this because that's a metal and a non-metal, so I know it's ionic to begin with. If we look at carbon and sulfur, carbon is 2.5, sulfur is also 2.5, which means if we subtract that difference, that's actually a difference of 0, which means the carbon-sulfur bond is actually nonpolar. Brings up a good point. You can't have two different elements that is going to share electrons equally. And this is what is sometimes referred to as the diagonal rule. They are diagonal of each other on the periodic table. One's further up, one's further to the right. They cancel their differences. They end up with the same electronegativity. We also see that with like nitrogen and chlorine as well. Now, to finish up here, before everybody packs up, you sometimes just need the general trend in electronegativity to help you without even the numbers. If I look at something like carbon and oxygen, for example, they're in the same row on the periodic table. Oxygen is further to the right, which means it should be more electronegative. So you don't really need the numbers. It should be a polar bond. If you look at sulfur and oxygen, they're in the same group, which means the guy further up in that group should be more electronegative. and it should result in a polar bond. So if you're comparing something that's in the same row on the periodic table or the same group on the periodic table, you really don't need the numbers, even though it'll probably be polar if they are in the same group. As long as they're diagonal of each other, then they may be nonpolar. Any questions on how to use electronegativity to help us determine bond polarity?